Hello again and welcome to this video lecture on estimates, estimators and minimum variance estimation. Let's start by stating the problem. Suppose that x and y are some jointly distributed random variables and we can measure y. We ask what is a good way to estimate x given y. In other words, we're looking for a function big X hat that takes in an observation of y, a measurement or a sample of y, that is to say, and returns an estimate of x. This is illustrated in this figure. An estimator is exactly this mechanism. The estimator takes a sample little y and produces a value little x hat using the function big X hat. Little y is a realization of the random variable y. It is the value of y for some omega. Given a value little y, the value little x is called an estimate of x given the fact that y is equal to little y. The function big X hat is called an estimator, it's a function. And here note that big X hat of big Y is a random variable. We define the estimation error as the random variable shown here. Both x and big X hat of big Y are random variables. The expectation of the estimation error is called the estimation bias, and the variance-covariance matrix of the error is called the variance-covariance matrix of the estimator. There are several ways we can construct an estimator, depending on what we want to achieve. Here we will present an estimator whose estimates have a minimum variance. Suppose that x and y are jointly distributed vector-valued random variables. They can be either continuous or discrete. We observe a realization of the random variable y. Define little x hat of little y to be a minimizer of the following optimization problem. Little x hat attains a minimum conditional expectation of the squared norm of the deviation from the true but unknown random variable x, given that y is equal to little y. We say that little x hat is a minimum variance estimate of x, given the fact that y is equal to y. We can show that this minimizer is unique, and it is in fact equal to the conditional expectation of x, given the fact that y is equal to y. The proof is as follows. First, we expand the squared norm of the difference x minus z. Next, we employ the fact that the conditional expectation is linear. Note here that the first term does not depend on z. And what we will do next is that we will complete the square of this part of the expression. To that end, we shall add and subtract this squared norm of the expectation of x given that y is equal to y, this yellow term. Let us focus on this part of the equation, which is the only part that depends on z. I will give you a minute for you to pause the video and think what this is. So this is the squared norm of this difference. We have managed to write the cost function of the given optimization problem as a quadratic function in z, and clearly the minimum is attained when z is equal to the conditional expectation of x, given that y is equal to little y. Lastly, we define the risk or quadratic risk of the estimate little x hat to be the conditional expectation of the squared norm of x minus the estimate. This is precisely the optimal value of the cost of the above minimization problem. The conditional expectation is the minimum variance estimator of x given y. The estimator, big X hat, is exactly this random variable. This is an unbiased estimator, as we can show using the law of total expectation. And we can also show that the expected value of the error, given that y is equal to any particular value y, is equal to 0. Moreover, no other estimator z has a smaller quadratic risk. Let's have a look at an example. Suppose that x and y are jointly normally distributed and have 0 mean and this variance-covariance matrix. This is the distribution of x. We measure that y is equal to 1 and we want to estimate x. The conditional PDF of x given that y is equal to 1 is shown here with a dashed line. The expected value of x given that y is equal to 1 is 0.8571. And similarly, for y is equal to 2, we can estimate x. The conditional expectation of x given that y is equal to 2 is 1.7143. The variance of this estimate is 0.4857, and in fact, it is independent of little y, as we can see. This is the joint PDF of x and y. To estimate x, given that y is, for example, equal to minus 0.5, means to slice this PDF along the line y is equal to minus 0.5. The conditional density function of x, given that y is equal to minus 0.5, is shown here with a dashed line, and it is a scaled version of the solid red line. I will leave it to you to think why this is so. The expectation of this dashed density function is the conditional expectation of x, given that y is equal to minus 0.5. So that's all about the minimum variance estimator. The next video will be an introduction to the Kalman filter, which can be seen as an application of the minimum variance estimator used to estimate the state vector of a dynamical system given available measurements. Thank you very much for watching and stay tuned. Goodbye.